right, good evening, everyone. Thanks for coming. It's great to see such a wonderful crowd here. So welcome to the Boston Lucene Solr Meetup slash AI Club Meetup, Boston. Lots of keywords there. So I wanted to welcome you from Fidelity. My name's Christine Venezia. I'm a program manager here at Fidelity, and we have an AI club that we run here. And Krishna Valaru is one of my ambassadors here for the Boston region. So we wanted to welcome you here today. Just a couple of housekeeping things. Men's room is right outside the door. The ladies' room is down the hall if you need it. Eat all that pizza, man, because it's just gonna sit if you don't. Make sure you get one of these really cool t-shirts. I can't wait to wear this. Yes. And thank you so much to LucidWorks for coming out tonight. I appreciate it. Anything you would like to say?
Yeah, please, actually, so I will just take 2 minutes of your time, between the speakers and, me, it is like just 2 more minutes. So welcome to Fidelity Investments, and just I would like to say that we were happy to host all of you today. And I work for asset management, advanced data analytics. That's on the slide here. So it is we help like portfolio managers and research analysts to pick stocks. So we work on many alternative data sets. We have like a kind of a startup mentality with mid company like processes and with a large company funding, unlimited funding. So think about that actually as a startup. And we have like great commute to the building, and we work in the same building, and also great view here as you have seen. So we have like 3 positions open. Like they are like really good positions, working with all different types of work. Last year we just worked on 200 different projects, 77 different, we delivered actually like to the business. Like this is really a great team to work on. We are kind of a like SWAT team. I had like 3 from in the meetups, like during these meetups, I had 3 of them. They are working awesome. They don't want to tell their names, but they are shy, but they are really great people to work with. So with that, actually, please reach out to me. You can we have like temporary, permanent, and also positions open with all of those. So with that, I will hand it over to Brant Anderson. Please welcome Brant.
All right, good evening, everybody. So Brant Anderson, I'm with LucidWorks. Just want to say a huge thank you for everyone showing up tonight. Hopefully people weren't restless waiting for the event to get started. There's a lot more beer out there, and I think there's a little more pizza. So thanks for eating the pizza. I was getting a little worried. So first of all, I want to thank the Fidelity team. So obviously they're hiring. I can attest they've got a great team, great people, some really amazing projects that we're working on here. So we have 3 speakers tonight. So I wanted to say that the event this evening is being hosted by Basis Technology as well as LucidWorks and Fidelity. So we have 3 speakers this evening. We have Trey Granger, who is from LucidWorks. First talk is going to be thought vectors in knowledge graphs and AI-powered search. A little bit about Trey. Trey is LucidWorks Chief Algorithms Officer. He drives the vision, practical application of intelligent data science algorithms to power relevant search experience for hundreds of the world's biggest and brightest companies. The guy knows a lot about search, a lot about artificial intelligence, and we're excited to have him here. He's also the author of several books, AI-Powered Search and Solr in Action, and he's extremely involved in research and journal articles and publications, and can cover a lot of different topics. So we're excited to have him here. So the plan is for him to speak for about 45 minutes. And then we have 2 folks from Basis Technology who are based just over in Cambridge, if you're not familiar with them. The first one is Gil Irizarry, who is their VP of Technology, VP of Engineering. He leads the text analytics team that builds plugins for Lucene and Solr to help boost precision and recall in multilingual search, as well as fuzzy name matching to overcome spelling variation and cross-lingual headaches. So Gil will be coming on speaking for about 20 minutes, and then we'll wrap things up with Philip Blair. Philip's also with Basis Technology. He's a senior research engineer. I apologize for the cheat sheet, by the way. He investigates practical applications for deep learning technologies for use in text analytics. He also leads Basis's technology machine learning infrastructure team focused on deploying cutting-edge algorithms into the field. I needed these notes because that's a lot of words, a big mouthful. So again, 45 minutes with Trey. We'll take a quick break, and then we'll jump in, and those gentlemen who speak, let's keep it interactive as they're presenting tonight. Ask questions, raise your hand. We'll have a couple mics that we'll be walking around with, and then we should have some time at the end also to do a little networking and ask some questions in general, and let's have some fun. All right, thanks.
All right. Welcome everybody. I am Trey Granger. That was a great introduction. I don't think I need to tell you about myself. I did want to, before I start though, so topic is thought vectors and knowledge graphs and AI-powered search. Before I get started, I wanted to do a quick survey of the audience. How many of you guys have worked with search engines? Okay, the majority. How many of you guys and girls have worked with Solr specifically? Okay. Okay, very good. I've got a few slides in here that are, well, how many of you have no experience whatsoever working with the search engine? A couple. Okay. I've got a couple of slides in here that are some introductory material. I might go through it kind of quickly because it sounds like the audience doesn't really need it for the most part. So, all right, we'll get started. So that's a mouthful, thought vectors and knowledge graphs and AI-powered search. I've been introduced, so don't need to know much more about me. You did hear that I'm the author of Solr in Action. I'm also currently writing a new book called AI-Powered Search. You can purchase it now, and once it's written, like a year from now, you'll get a copy. So please, I've got a nice AI-Powered Powered Search t-shirt on too, so buy the book so I can quit wearing this thing. Just kidding, just kidding. But yeah, as the book is written, if you buy it, you get the chapters as they're written. You can provide feedback and get insights, so definitely check it out. Also, I don't know if anybody in here is on Twitter, but I've got a couple of free books to give out. I'll give maybe 2 out to people who ask great questions at the end of the talks. Or if you have a tweet I really, really like, then I'll send you a code for a book too. Hint, hint, nudge, nudge. Okay, so the agenda for tonight, I'll quickly tell you about LucidWorks, go over what AI-powered search is, talk about thought vectors and what they are, talk about doing vector search in Apache Solr, talk about knowledge graphs, a little bit of philosophy of language, semantic knowledge graphs specifically, as implemented in Solr, and then how to do graph-based search leveraging some capabilities in Solr, including the semantic knowledge graph and the Solr text tagger, and do some demos at the end. So that's a lot to get through. I'm going to go kind of quickly, but feel free to raise your hand if you have a question at any point. So LucidWorks, we've got about a little over 300 employees spread across the world, offices all around the world. We historically have employed about 40% of the active committers on the Apache Solr project, and historically have contributed about 70% of Solr's open source code base. We also sponsor Activate, which is the Search and AI conference, and just had that a little over a month ago. We also, from a software standpoint, we do a lot of development on Apache Solr, but we also have commercial search technology, a product called LucidWorks Fusion, which is composed of Fusion Server, Fusion AI, and Fusion App Studio. I won't talk much about it tonight, but I'll hint at it in a couple of places. But definitely, it's built with pride on open source technology. Apache Solr and Apache Spark are at the core of Fusion, and then Fusion adds all of the other plumbing and orchestration and infrastructure, and really the AI and machine learning capabilities you need on top of Apache Solr. It allows customers to personalize search with applied machine learning, and it's proven on the world's biggest information systems. One of our largest customers is Reddit, who I think they're like the 4th largest website in the world, so we operate at very high scale. So from the title, we talked about AI-powered search. The question is, what is AI-powered search? And there's a lot of buzzwords. I think the folks in this room can probably differentiate between these more so than your average folks out there. But you've got buzzwords like AI, AI-powered search, deep learning, machine learning, data science, neural search. And the question is, if you want to ask what the difference between these are, the difference between machine learning and AI, as Matt Valeso so eloquently said, is if it's written in Python, it's probably machine learning. And if it's written in PowerPoint, it's probably AI. I've found this to be true in practice. But the reality is we can easily dissect what these words mean by looking at a simple Venn diagram. So artificial intelligence is an area within computer science that focuses on trying to create systems that mimic human behavior. That's pure and simple. Machine learning is a subset of artificial intelligence that specifically focuses on applying math to data to try to automatically learn more information about the data and learn how to mimic human behavior. And then deep learning is a subset of machine learning that focuses specifically on leveraging deeply nested neural networks. So deep learning is a subset of machine learning, which is a subset of AI. Going further, though, when you talk about data science, obviously there's an intersection between all of these, but there's other things in data science that data scientists do beyond this. Things like data visualization, things like really digging in and understanding the business needs and use cases and being able to marry those together with these AI technologies. Then, of course, you've got search, similarly intersected with all of these. There's a lot in search that intersects with data science and machine learning, but not everything, right? Search is very interdisciplinary. There's a lot of focus on scaling systems and lots of other needs in search. And so when we talk about what AI-powered search is, we're really talking about this intersection right here in the middle. And to be concrete about it, if you look at this outer section, which is the full AI circle, you've got things like question answer systems, virtual assistants, chatbots, rules-based relevancy, and so on. These are all things that have components that don't necessarily have to leverage machine learning and deep learning, but they often do, but they don't have to. You could build, for example, a question answer system or a virtual assistant or chatbot purely based upon rules, though the best ones obviously these days leverage machine learning and often deep learning. The next circle down is the intersection of search and machine learning. This is where you get into fancy capabilities like signal boosting models, learning to rank, semantic search, collaborative filtering, personalized search, content clustering, NLP and entity resolution, semantic knowledge graphs, document classification, and so on. Again, these things can leverage deep learning because it's a subset, but they don't have to and often don't. And then finally, this middle circle, which is purely the intersection of search and deep learning, you get things like neural search or neural IR, word embeddings, vector search, image and voice search, and so on. These are things also that in some cases can be done with techniques that don't involve deep learning, but they very rarely are because deep learning generates the best inputs and generates the best models for doing these things. So when I talk about AI-powered search, when I'm writing in the book, these are the things that I'm talking about and trying to integrate these all together into an intelligent search system. Tonight, specifically, I'm only going to touch on a few of these. So semantic search, NLP and entity resolution, semantic knowledge graphs, a little bit about question answer systems, though not much, some rules-based relevancy. And then, of course, we're talking about thought vectors and vector search. So we'll have word embeddings and a little bit of neural IR in here as well. So I've got some slides on search engine basics. Since 95% of the audience knows this stuff, I'm going to spend 10 seconds going through these. Search engines have an inverted index. They're very, very fast. Google is able to search through billions and billions of documents instantly or near instantly because they pre-index all the answers to the questions. That's what an inverted index is. You can type in a keyword and match a list of documents in which that keyword appears. If somebody searches a multi-word query like Apache Solr, like we have in here, you go to the inverted index, you look up all the documents that have the word Apache in them, all the documents that have the word Solr in them, you do an intersection, that gets you the document set with Apache Solr. Then of course there's scoring that comes into account. So once you run a search, you find all the documents that match your keywords, you then have to rank all of the documents based upon how related they are to the query that was typed in. So this is the default relevancy text-based relevancy scoring calculation that happens in Solr. It's called BM25, and it enables you to, I'm not going to get into the math, but it enables you to find the documents effectively which best match the query from a text string match standpoint.
Hey, does anybody want to get into the math? I'm just kidding.
I'm happy to go through this stuff, especially for the like 4 or 5 folks who don't have familiarity with search. I'm happy to walk through this in more detail later, but I'll keep it moving for everybody else. Apache Solr is an open source search project based upon Apache Lucene. Apache Lucene and Apache Solr are both part of the same project that is run by the Apache Software Foundation. And there are committers who are able to contribute code to this based upon being great people, great engineers, and their contributions to the project. We have at least one committer in the audience. David, smile over here. I think just one. So you can ask him questions later if you want about what that means and how cool it is. But Apache Solr is an awesome project. And it's used by 90% of the Fortune 500 to power enterprise search needs. Key capabilities in Solr, which again I'm assuming most of the people in this room know, so I'm going to go quickly through them, are things like multilingual keyword search, relevance ranking of results, faceting and analytics, highlighting, spelling correction, autocomplete and type-ahead prediction, sorting, grouping, deduplication, distributed fault-tolerant scalable systems, geospatial search, complex function queries, recommendations with more like this, graph queries and traversals, SQL query support, streaming aggregations, batch and streaming processing, highly configurable plugins, learning to rank, building machine learning models, and much more. I'll go a little slower now. So what is natural language search? So we just talked about running keyword search, hitting an inverted index, and finding documents, ranking them, and returning them. Natural language search, instead of just typing in keywords and matching those, is the process of effectively asking the search engine a question like you would ask a person a question. So something like, in this question and answer demo we have from LucidWorks, can my wife drive on my insurance? I'm not looking for documents that have the word can, my, insurance. I'm not looking for documents that have those. What I'm looking for is the right answer to this question. And so, building a system that can rank that. For example, the top answer here is, can my wife drive on my insurance? The answer is yes, unless your husband has coverage on a separate auto insurance policy. And then it goes on to about some other stuff about Wisconsin. Maybe that's not the best answer. I don't know. So that's natural language search. So then the question is, what is the thought vector? Does anybody in the audience know what a thought vector is? Nobody. Awesome. I love that. Okay. So who knows what a vector is? All right, perfect. Okay. So a thought vector, imagine you have a document, which hopefully you have a lot of documents. There's different parts of the documents. You've got words, you've got sentences, phrases, paragraphs, and the entire document. In search, traditionally, we break apart the document into a bunch of keywords and we index those keywords. Sometimes we will take the keywords and create phrases and index the phrases, but generally speaking, we're dealing with things on a keyword level. What thought vectors are taking those individual pieces of documents and mapping them to a vector that represents the meaning associated with those terms, phrases, etc. So thought vectors are things like word embeddings. So let me look at every single word in the document and let me generate a vector that corresponds to the sort of semantic meaning of this term. Sentence embeddings are another kind. It's, let me take an entire sentence and map it to a vector that is associated with the meaning. Paragraph embeddings, obviously same thing, but you're dealing with an entire paragraph. And then of course you can take an entire document and map that document to a vector associated with the meaning. This is a little bit abstract if you're not used to thinking about things in terms of vectors. The data scientists in the room probably obviously know what this is. But let me sort of dive into where this comes from. So a thought vector is purely a vector that represents some meaning or thought that is associated with parts of your document. And there can be many different vectors throughout your document for different pieces and combinations. So let's take that inverted index that we talked about earlier and the way that search normally works and just think of it as a vector for a second. So on the left here, the yellow, these are queries somebody might type into the search engine. And on the right, these are terms that would be in my inverted index, the pink columns. So in the first row, if somebody searches for cappuccino, notice that cappuccino doesn't exist in my inverted index. There's no pink box associated with it. So you have a vector that's all zeros. There's no entries in it. For apple, apple does exist in my inverted index, and it exists in one of these entries. So there's a 1 there. Juice exists in my index, and there's a 1 there, etc. All of these are individual terms. If they appear in my index, then there is a 1. If they don't appear, then it's all zeros. But effectively, everything is a 0 except for the position in which that term appears. This is one hot encoding, if you want to think of it that from a sort of data science standpoint. But what I've effectively done is gone from thinking of this as a keyword match to thinking of each of these terms as a vector where there's one entry in that vector amongst all possible values that there could be. Of course, you can do math with vectors. So what if I want to search for apple juice? So going back to my set intersection slide I went through earlier, if I want to take the vector for apple and the vector for juice and add them together, now I've got a vector for apple juice which matches both of those terms. And so now if I think of in terms of multi-term searches, now I'm generating a vector not for a single term search but for multi-term search. The word latte doesn't exist anywhere, cappuccino still doesn't exist, but now apple juice has two entries in there, one for apple and one for juice. That vector has two positions filled. This is probably becoming very apparent what's going on, pretty obvious. But what I'm doing is I'm thinking of each of these words as each of these queries as a vector that has different pieces filled in. The size of the vector is equal to the number of terms in my inverted index. So it's a very, very large vector, very long vector. In linear algebra, we've got the ability to do dimensionality reduction, which is instead of having a vector that is the size of all of the terms in my index, what I can actually do is I can start taking, instead of all the terms in the index, maybe I can break the index down into a smaller set of categories, and then I can associate some value with that category. And so now so what I'm doing here, you'll notice that now my columns, instead of being terms that are text matches, they're more conceptual. I found documents that map into these categories. So the categories here I've got, I just made these up, are food, drink, dairy, bread, caffeine, sweet, calories, and healthy. So if I would have taken all of my food documents and tried to reduce the dimensions down to meaningful things that represent a decent portion of the documents, this might be what would happen if I took that n-dimensional vector where the number of dimensions was every term in my index and broke it down into, what's this, into 8 different values or 8 dimensions in my vector. And so what you see now is apple juice is not food. It is a drink, so it gets a score of 5. All of these are between 1 and 5. And usually you'll use floats instead of integers, but it's much easier to look at as integers for a presentation. So, apple juice is a drink, gets a 5. It's not dairy, it's not bread, it's not caffeine. It is sweet, gets a 4 for that. Has a lot of calories, gets a 4 for that. And it's, reasonably healthy, some say. Cappuccino, again, not food, it is a drink, etc. If you go through all of these, you'll probably say, yes, these pretty much make sense. Let me just find donut. Donut is food, is not a drink, has maybe a little bit of dairy, definitely bread, no caffeine, very sweet, lots of calories, not healthy. So you get the idea. This is now how I'm representing each of these terms by these vectors. And if I then take these vectors and look at them on this next slide, I've got my vector laid out for each of these terms. What I can actually do is do similarity scoring between each of them. So, for example, by the way, this is just a cosine similarity. So all I'm doing is, figuring out the distance between the vectors. If I search for the vector for apple juice and compare it with the vector for apple juice, I'll get a 1 if it's a great match and a 0 if it's not. So now what I can do is I can take cheese pizza and compare it with all of the other vectors. The first table you see there, and I see that I get a 0.99 as my ranking for the similarity of cheese breadsticks with cheese pizza. Cinnamon breadsticks is the next most related. Donut is the next most related, then latte, then apple juice, and the least related thing to cheese pizza is water. Similarly, if I search for green tea, the most related thing is water, followed by cappuccino, and then latte, and then apple juice, and then soda. All of those are drinks. And then donut is the least related to water. So this is a different way of scoring. Instead of thinking of things in terms of keywords and finding the exact text match for a keyword, or maybe some slightly modified match if I'm using stemming or some sort of text analysis, what I'm doing here is mapping the terms to a vector of meaning that represents them and then doing scoring based upon the similarity of those vectors. So there's some performance considerations associated with doing this. So vector scoring, first of all, is slow because unlike keyword search, which we talked about, Google being able to search through billions and billions of things instantly because they've already pre-indexed all the answers, with vector scoring, you have to actually take each query's vector and compare it with every document's vector in order to figure out which ones show up at the top. In other words, you're not matching on the vector, you're scoring the vectors and you're sorting. It's a ranking problem. Therefore, because you have to go through every single document and score all the vectors in the documents, this becomes very slow and doesn't work well at scale with lots of documents. So a solution to that is to use what are called quantized vectors, where quantization is the process of taking those vectors that we just looked at and mapping them to a discrete value. So instead of being a range of numbers, I'm creating some token that represents the value of that vector. So the whole vector gets mapped down into a series of one or more tokens. And I'll show you what that looks like in just a bit. But effectively what happens then is I can index tokens and search and match on those tokens and find an approximate match to what the vector scoring would give me. In other words, instead of having to score every single vector, I can search on certain tokens, filter down to those tokens, and know with reasonable certainty that I'm getting a pretty good match for what the vector scoring would have also returned back to me. I'm searching in a similar vector space in terms of how these tokens are clustered together. So it's effectively like a KNN problem where I'm trying to find the nearest neighbors to this quantized vector term. And generally speaking, there's going to be the same documents that would score high for a vector similarity calculation. So typically the recommended approach for doing vector scoring and search is to actually combine these two techniques. So if I can create a quantized vector or create terms in my index, search and filter on those terms to do sort of a KNN match to find a set of, 1,000, 10,000, some small number of documents that are likely to contain the best matches, I can then do a follow-on re-ranking pass and do an actual vector similarity score between each of those documents, between the query and each of those documents to get the same answer that I would have received had I just done the slow vector similarity calculations across all of the documents to begin with. And so in practice, when you see vector search implementations, this is the approach that most of them follow. So this approximate nearest neighbor technique we're talking about to create these terms, these quantized vectors, there's a bunch of different techniques that have been benchmarked. These are sort of like all the state-of-the-art algorithms out there. Interestingly, there's one in here, if you look at the top, I think it's I don't know if it's the blue or the green, but the one at the very top that's performing the best, there's this one called HNSW. This is a specific implementation that uses hierarchical graph stuff internally, but it's the implementation that seems to be the most scalable to get you the highest recall with the best scale. And we've just started, by we I mean smarter people than me, have just started implementing this in Apache Lucene, which means whenever that's done, Lucene would hopefully have the most performant, best benchmarking implementation for doing this that's out there today. And I'll talk about that in a minute. So I just talked about how vector search and scoring works. The question is, okay, but can you actually do it in Solr? And the answer is kind of. So you can. So one option that works today is leveraging streaming expressions. So who knows what streaming expressions in Solr are? Not as many people. Okay. So in Apache Solr, when you do a normal search, you send in queries, keywords, you can facet, highlight, etc. Works really fast, uses the invert index, etc. There's another capability that's typically used more for analytics called streaming expressions, which allows you to effectively do kind of like distributed functional programming, where you can pull in streams of data from the index and process them and then pass them on to other streams into other expressions for them to be processed. And so I'll show you an example of that in a second, but you can do vector similarity calculations with that. So for this example, I'm taking all those food documents I just showed you, and I'm sending them to Solr. I've got documents that have an ID, a name, and a vector field. The vector is just a multi-valued float. So it's just a float field, but there's multiple values in it. And the way streaming expressions work, they can actually, for those of you who know the internals of things like doc values, streaming expressions can actually use the stored values associated with whatever you pass in. So whereas doc values actually are sorted based upon the value itself in the index. So you wouldn't maintain the order of the vector. It's really important to maintain the order of the vector here. So leveraging the stored version is how this is able to work. So this wouldn't work with a typical search if somebody just indexed a bunch of floats, but it does specifically with streaming expressions because they can use the stored value. I'm going to stop geeking out on that piece because I lost most of the audience there. Coming back up now, send these documents into Solr, and once I've done that, this is the streaming expression that will get you your vector similarity score. So hopefully you can read that. The screen's pretty big here. But I have I'm going to start from the middle of this expression. There's a search expression, and the search actually is the third line down in that top box. So I'm searching on the food collection for, the query is find all documents. I want to return the ID, the vector, and the name fields, and I want to sort on the ID. And then after I've selected that, I also want to now I want to perform a cosine similarity expression or function on that vector, and I want to compare that vector that came back on that document with another vector. It's an array here that is just an arbitrary other vector I'm passing in to do the score. So that is my query effectively. It's something like a donut because donut came up really high. So some sweet bready thing. And I'm taking that vector, which is, instead of passing in a keyword query, that array, it says 5.2, 2.0, etc., that is my query. That's going in. I'm doing a similar cosine similarity with the actual vector in each document, and then those scores are being returned. And then the select returns the top 5, and then the outer function you see here at the very top, the first line is the top. I'm saying return me back my top. Oh, sorry, this is where I'm doing the top 5. Return me my top 5. So I'm finding the top 5 highest ranked results for that cosine similarity function. And so my donut-like thing I'm searching for, return donut, cinnamon breadsticks, and cheese pizza. So just an example of actually implementing vector search and scoring in Solr. The downside of doing that is that you have to move over to use the streaming expressions capabilities in Solr, which are more geared towards analytics and not as much geared towards real-time search with faceting and all of those things. So there's another way to do this, which is a patch I implemented last week because I was frustrated I couldn't do this. So it's not part of Solr, and it's not very efficient, and it's not great yet, but it works. And it's the streaming expression query parser. So the way this thing works is I run a normal search in Solr, and I apply a filter, and that filter is a streaming expression. So that same expression you saw just a second ago, I'm running a normal search, and I'm passing that streaming expression into a streaming expression query parser. It's finding those results. I'm telling it to return me the top 5 ranked results, and then it is filtering on those results in my main search results set. So then I could do faceting, highlighting, all the normal things that I would do with search. I haven't implemented any ranking on what comes back, so this is purely a filter. So you'll notice that the results are coming back, donut, apple juice, cheese pizza, cheese breadsticks. Even though cheese breadsticks was the second best, the result set here doesn't really know that, but it is still the top 5 being returned. And this sorting we could probably get in later. So that's another way to do it that can actually allow you to use that same expression in a normal search query. Third option. There is a Solr vector scoring plugin that was implemented. It's got an Apache 2.0 license on it, so you can definitely use it if you want. Same kind of thing. I'm using the example that's from that plugin's repository, but you basically pass in the documents just like I did before. Here's a vector, but in this case the vector isn't a float field that's multi-valued. The vector is a text field, and there's an analyzer on that field that is storing a term associated with each position in the vector. So you see in each vector there's 0, it's got a value, 1 has a value, 2 has a value, etc. And then internally it's storing the vector's value for each dimension, for its position, as a payload in Solr. But then you have the ability to do a vector scoring query parser, which can actually do the vector scoring and return you back similar results. So caveat, this isn't super fast because payloads can be pretty slow, especially if you're having to go through all the documents, but it does work. There's some ways to improve this from a performance standpoint, but it functionally works. And then option 4, which is where it starts getting interesting, is something that it does actually combine a quantized version of the vector with the vector scoring. So this is a fork of that last project that we just looked at, but this fork adds an LSH hash to the function, which effectively gives you a token that represents that vector. So you can see what a quantized vector looks like here. So same thing, I'm passing in the first 2 documents that you saw in that last document set. So ID number 1, ID number 2, there's the vectors. I send in the request. It looks exactly like the one I had before, same vector function, but I have LSH equals true being passed in. And then I have a re-rank docs equals 5. So what it's actually doing is it's finding a quantized version of that vector that was passed in, searching on the LSH hash associated with that vector to find the ideal results, and then it will rank those. So these are the results that come back when I send that in. Notice that document 1 came back because that was the one that actually, I think it was probably the exact same vector I searched on. But you'll notice that the vector that comes back, that hash-looking value, is the LSH, and that is the quantized version of the vector. And then, that was the vector that, as it got implemented. Then the LSH hash has a bunch of dimension values that get searched on in order to try to find where sort of in vector space this document would match. So this is much faster than the last example you saw because you don't have to score every single document relative to your query vector. You first do a filter to get a nearest neighbor result set that probably has 90-95% of all the values that you would get from your vector scoring, and then you re-rank those values as they come back. Same caveat as before. This uses a text field with analyzers, and it uses payloads, so that part is still slow, but because you have the LSH implementation, you're only re-ranking some number of documents, it's going to be a lot faster at scale. And then option 5, which is a work in progress that really just kind of got started last week, is implementing first-class vector fields in Lucene and Solr. And so there is a Solr JIRA associated with this, which is Solr 12890, to implement vector fields and all of the sort of search and query and scoring semantics associated with that. And there's Lucene 9004, which is approximate nearest vector search in Lucene to implement that HNSW ANN approach I told you earlier, which was the fastest and most performant. So that is in process, and I'm going to be working on the vector search and Solr piece of that to try to pair those together. Yep. What's up?
Does Solr's patch on the right, does that have to come in Lucene before the vector search and Solr will be?
Sure. So the question was, so Michael Sokolov is implementing the approximate nearest neighbor search in Lucene, hopefully with help. The question was, does that need to be implemented before the Solr version can be implemented? And the answer is, there's 2 aspects to vector search. One is this, like we talked about, one is this approximate nearest neighbor quantization to be able to filter down on tokens to make it fast. And then there's the re-ranking piece, which is the actual vector scoring. So for the re-ranking piece, no, that just needs the ability to store a vector in a field and then to do the scoring on top of it, and that actually shouldn't be that much effort to implement. So that piece can be done now. For the nearest neighbor search, there's simpler ways to do it than what Michael's doing, which could probably be done sooner. There might even be some current implementations that could do it with an update processor, like LSH kind of stuff. But his implementation should be fast and performant and highly accurate. So there's no dependency, but whenever his stuff goes in, it will make it better. Yeah. And so another thing to talk about here is vector encoders. So I sort of glossed over the fact that I had some vectors that you were looking at earlier when I created those food vectors with the 8 different categories. I just made those up. In the real world, I need to be able to take arbitrary queries and arbitrary documents and arbitrary sentences and paragraphs and map those into a vector. So how do you do that? The answer is you leverage a library that can do that for you, or you train one. So most of these popular libraries, you've probably heard of a lot of these, things like BERT, Elmo, Google's Universal Sentence Encoder, Word2Vec, should be a C there, Sentence2Vec, GLUV, FastText, etc. Most of these leverage deep learning in some way to be able to take your content and automatically learn vector representations of language that can do things like understand when certain terms in a query have to do with a question and somehow encoding in the vector the idea of this is a question, or this is the answer to this is a person, or relationships within the vector. And so being able to leverage deep learning to automatically learn encoders that can take documents and queries, etc., and map those into vectors, both for document understanding as well as query understanding, is the way to go here. But that being said, keyword search isn't dead. In fact, vector search is an additional tool in our arsenal, but keyword search is still very important, and I would argue that there's a level of search even beyond these two that needs to be considered as well. And so I've got a couple of different query types over here on the left. Yep.
Is there the possibility of extracting a keyword and turning that into a vector?
The question is there a possibility of extracting a keyword and turning it into a vector?
Yeah, so like instead of like a keyword, so if you have a document, extract all the keywords out of the document and share a vector.
So if you have a document, extract all the keywords out of the document, then you get a vector. Yeah, so the question is, how do you encode a document into a vector, really? Some techniques take all of the words in the document and then get the vectors for those and sort of average them together. That tends to work out pretty well. Sometimes you'll do that on a per paragraph basis and then average those together. There's different approaches. Trial and error. The encoders on the last page, the deep learning based ones, tend to do a pretty good job of figuring that stuff out when you throw documents at them, but not all of them, actually. So yeah, there's different techniques. But averaging vectors together of a bunch of words in a sentence to get the meaning of the sentence is a very common technique. There's probably better ones. So looking at these different query types, this first one I have up here is obscure keyword combinations. So something like software or hardware and ENGINE star. So the wildcard search there. A vector search encoder that was trained on natural language content is not going to really ever see that natural language content or know what that means, and even like the wildcard. So in that case, the vector search is probably going to do a pretty poor job. It's not really understanding the structure, the Boolean structure of that, and keyword search is going to do well, because this is basically a keyword search query. The second example, a natural language query. Can my wife drive on my insurance? Keyword search might get lucky because it might match the right words and score them appropriately, but it'll probably fail, especially if you're anding all the terms together, because you're not really expecting all those to be there. So I wouldn't count on keyword search working. It might get lucky. Vector search, though, should succeed because it's going to understand that wife is associated with the husband, so I need to be looking for documents about husbands driving, or could be wives these days, whatever, could be anybody, but most likely in the documents it's going to look at, it's going to extract out whatever features are going to be the most impactful for answering this question, and understand that insurance might have other words associated with it as well. So it's a fuzzier search, a semantic search, a search on meaning. Fuzzy language queries are things like famous French tower. So same kind of thing. If I do a keyword search on this, it's not going to match Eiffel Tower, but the vector encoding is able to learn from your content that French tower, Paris, Eiffel, these things are all related semantically. They're in a similar vector space, and it's going to be able to match these things and score them appropriately. But then this last example, neither one of them really do well. So something like popular barbecue near Activate. So Activate's our annual conference my LucidWorks puts on. Yep, question?
I just wanted to, because I wanted to wait for you to get through the call so I could speak to your question. You said that people extract, they encode a keyword in a query and turn that into a vector. And I was going to say, based on those examples, the way the state of the art today, and I think Trey probably knows more about this than me, but the state of the art today is that we know that a word is vectorizing the whole query together, because that's going to tell you more than one individual keyword, right? And sorry. And now, in the case of BERT for like Latin script languages, so like English, French, European languages, like BERT is doing the bidirectional encoding the best, and Elmo, I think, has a slight lead in the East Asian languages. I think mainly Chinese and just Chinese, I think, but maybe some of the other ones. But like, it's all about bidirectional encoding today. That's the state of the art, and it's the context. So it's multiple words and then encoded bidirectionally, because it feels French, like famous French tower in Spanish. I don't know, La Torre Famosa Francesa or something. La Torre Famosa Francesa. It's not in the same order, and it means something different if you are just encoding it in one way, or if you're just encoding one word, it means nothing. So yeah, I just wanted to answer that for you, so you knew. You could check those out.
Thanks, Marcus. Cool. All right, so this last, go ahead.
I have a question with regard to the natural language queries. And do you really think that a vector search based on call sign similarity will actually solve this problem? Because to me, the best document that you will return would be the document contains exactly the same sentence.
So the question is, do we really think cosine similarity is going to return the best results here? Because the best result would be returning exactly the same sentence.
Yep.
I think the important thing to realize here is that the goal is not to match the sentence. The goal is to find the answer. And so the answer might not have any of those words in it. The answer might be about a husband being under a policy, for example. So the point with the vector representation is that it doesn't care about the actual text that's used. What it cares about is the meaning associated with the query and the answer. And so that's why the vector representation, even like the French tower example, it is very, very similar, and it will find the right answer because it's a meaning match, not a sort of syntactic match.
Because to my understanding, for example, for the BERT pre-trained model, people are not using direct call sign similarity to measure the distance. They would rather concatenate and get a similarity score by feeding into the model as a single sentence. So I was just curious if the call sign similarity can be the ultimate function to measure distance of two vectors.
Yeah, so yes, you're absolutely right. The point is that using a cosine similarity to relate things isn't necessarily the best way. If you do have a deep learning model, for example, and you can pass the values in there and get a different answer back, then oftentimes that can perform better. Yeah, I'm trying actually in this talk not to get too much into the implementation because we've got the basis talks coming up, and they're going to talk more about some of this stuff. So, but yeah, you're right.
Thank you.
Yep. Structured relationship queries, this last example, something like popular barbecue near activate, or who is the father of the niece of the brother of the person who lives down the street from the guy. If you start thinking of language in terms of structure and relationships within your queries, at least current vector search approaches and even these neural nets don't hold a candle to actually having a knowledge graph. So if you've got a knowledge graph where you actually understand things in your domain and can relate them together and build search that actually syntactically understands those relationships and parses them, this still adds another layer on top of basic keyword search, vector or semantic similarity search, and then something which can actually understand the real relationships and structure and intent behind this. Because the reality is in this query, popular barbecue near activate, what I really want to do is find activate, figure out what venue it's at, what latitude and longitude are associated with that, filter down those results, and then find all the barbecue places within that area, and then sort them based upon which ones are the most popular, something like that. But all of that, I know in my brain, but at least modern neural nets don't tackle this problem very well. They handle it one or two levels, but once you start getting more structure and get multiple levels deep in terms of the semantic parsing, they tend to fall over. So that leads into, that's the sort of vector search part. And so then that leads into this idea of a knowledge graph. And I'm going to skip ahead a couple of slides, but to give you just some simplistic definitions, because people often get confused between, like what is a knowledge graph versus a taxonomy versus an ontology. At the very high level, they all have distinct meanings, but they also overlap because people use the terms interchangeably in some instances. I'm not going to go into the details of the slide, but let's just put it this way. A knowledge graph can subsume all of those other pieces, meaning you've got things like alternate labels and synonyms, which allow you to map terms to other terms with similar meanings. You've got taxonomies, which allow you to look at sort of hierarchical relationships between things. Ontologies, which map arbitrary relationships between kinds of things, and then a knowledge graph, which also infuses your real data points inside of that. So for all practical purposes, when I say knowledge graph, I'm really including all of these things in as sort of one larger system that understands terms, entities, phrases, relationships, et cetera, within a domain. And one of my favorite quotes, you guys have probably heard the quote, all models are wrong, but some are useful. It's from George E.P. Box. The full quote is, all models are approximations. Essentially, all models are wrong, but some are useful. However, the approximate nature of the model must always be borne in mind. And so, as search engineers and data scientists, et cetera, and just software engineers in general, we often have a tendency to try to put things into boxes. We have a tendency to say, this word goes in this category. I'm going to create a classifier, and I'm going to have 100 classes, or 1,000 classes, or 1,000,000 classes, and I'm going to put everything into one of those. But when you do that, you also are limiting down your result set, because some of those things might belong into multiple categories. And so similarly with knowledge graphs, a lot of times people will build out knowledge graphs and they'll put entities in them where that entity has one node and one meaning, and there's connections. But especially when you're dealing with natural language processing and natural language understanding, terms and phrases have unique contexts and unique meanings within those contexts. And so the question is, from a search standpoint, what kind of a knowledge graph can help us solve the kinds of problems that we deal with in search use cases? And so, those problems, there can be all kinds of unstructured data we deal with, but typically we're dealing with unstructured data. And when we say unstructured data, most of the time we're talking about text. And so I don't like the term unstructured data. I think it's a misnomer. In my mind, when you're dealing with text, you're really not dealing with unstructured data, you're really dealing with hyperstructured data. You're dealing with a graph that contains much more structure than typical structured data. And so, in a traditional, SQL database, for example, you might have, discrete values or IDs, continuous values and keys that can join, discrete keys. They're called foreign keys that can join values between tables. But similarly in text, if I look at this text I have on the screen, Trey Granger works at LucidWorks. He spoke at the Activate 2019 conference, et cetera. If I break that down into multiple documents, where each of these boxes up here is a document, I've got an image, I've got voicemail, I've got a video over here. That video happens to have my name in it. All of these think of these as 6 documents on my search engine. What I can actually do is start to think of this more like a graph and like structure. And so, for example, I see the word activate occurring in 2 of these documents. And so I can kind of think of that like a foreign key. Like if I had a database with a key in 2 different tables, I could join on that. In text, I could similarly join on that because if this word has the same meaning, then it's a foreign key between 2 pieces of text. If I look at this, I see Trey Granger and Trey. Those both refer to me. They both refer to the same entity. If I can do some sort of entity resolution, now I can use those as a fuzzy foreign key. If I go a step further, I look at the he, his, a picture of me, my name in that, this written out in that video. All of these refer to the same entity, so I can think of this similar to how we think about structured data, that the structure is within my text. But not so fast. This guy, if you ever go to Google and search for me, comes up. It does. Every time so first rule is don't ever Google yourself. But the reason is because, this guy, his name is spelled exactly the same way as mine. This is a picture from the movie Jaws, by the way, so it's not actually the guy. But, this is an example of polysemy or an ambiguous term. Trey Granger, you think it's unique, it's not. Some other guy's got my same name. And so if I take all of that together, just from these couple of pieces of text, these few documents, I have this giant graph of relationships. Places, people, dates, and like all of these things. And then, that other guy's he's disconnected from the graph. He's up in the top right. But these are all just from a tiny amount of text, like, 3, 6 documents. How many documents do you guys have in your search engines? 6. More than 6. Hundreds, thousands, millions, some people billions. Few people have trillions in Solr. So this giant graph of relationships, the question is, how do we easily harness the semantic graph of relationships within our unstructured information? And so we've got something in Solr called the semantic knowledge graph. And at the very highest level, it makes use of 2 data structures in the search engine. One is the inverted index, which you talked about earlier, which allows you to look up a term and find a set of documents associated with it. And the other is a forward index that's represented by doc values in Lucene, which allows you to go from a document to a set of terms. And so if I can go from terms to documents and documents to terms and terms to documents and documents to terms and keep traversing through those relationships, I have a graph. And so the way this works in practice, I've got a term up here, the skill of Java. It exists in a bunch of documents, and then I can find those documents and then go find other skills, other terms in the skills field associated with those. And I can then traverse multiple levels deep to find all the terms most associated with the skill of Java, and then find all the job titles most associated with that, assuming I've got these fields in my search index. Then I can also score the relationships. And so we've got a scoring function in there that allows me to, say I ran a search for Hadoop and I got a bunch of terms back, like B, Hive, Java.NET, teacher, registered nurse. I can actually semantically score those based upon the co-occurrences of these terms within documents to say that the word Hive is very, very positively correlated with Hadoop. The word Java is positively correlated, but not as positive as Hive. Teacher is negatively correlated. Typically, documents about Hadoop aren't also about teachers. They don't mention the word teacher, and registered nurse has an even greater negative correlation. And what I can then do with that is take my text and effectively facet, but I can facet with a semantic score based upon the relationship. So for example, whereas a normal search engine in Solr, you run a keyword search and you find a list of the top ranked documents matching that query. With the semantic knowledge graph, you're running a query, a keyword search, and you're finding the top other terms, the top other keywords that are most related to that keyword. And so if I just index a bunch of random text from the Stack Exchange health data set, and I search for the word Advil, the semantic knowledge graph returns me back, okay, well the most related things to Advil are Advil, Motrin, Aleve, naproxen, ibuprofen. Yep.
Is there an option for the knowledge graph to set it up as like a directly acyclic graph?
It's a DAG. Ask me after, just for time. Let's talk
thanks.
after. Let's talk after. Thanks. So you can take these terms and, for example, take a document, extract the phrases out of the document, and then score those. And so this document on the left is a job posting for a UI developer at LucidWorks, and the top most relevant terms in that document are JavaScript, CSS, AngularJS, semantic HTML frontend, and web standards. I've pushed down all of the content which is not specifically related to this document or not important to this document, and I've returned back a list of the things that are important. I'm going to skip over a couple of slides just for time. But one of the interesting things that we have to deal with, so that guy who had my same name with the picture from Jaws, that was an example of ambiguity. If I take the word driver and architect, for example, this is some work I did a few years back where we were mining query logs. But basically, there's 2 distinct meanings of the word driver. I've got like a vehicle driver versus like a software or hardware driver. And for architect, I've got sort of a building architect versus a data or software architect. And so one of the techniques that we can use to mine these is to figure out these meanings is the semantic knowledge graph. And so I can do things like search. So what this query to the semantic knowledge graph is doing is it's saying I'm going to search for the word barbecue. And then with the semantic knowledge graph, I want to return the top 2 categories that are the most semantically related to barbecue. And then within those top 2 categories, I want to find the top 3 terms that are the most related to barbecue within those categories. And so what I get back is, barbecue is the most related to the restaurant category. And within the restaurant category, the meaning is barbecue, brisket, ribs, and pork. And the second most popular, most related category is outdoor equipment. And within the outdoor equipment, barbecue means barbecue, grill, charcoal, and propane. This is a term vector. So we talked about numeric vectors earlier, where I had ones in each position. You could think of this the same way, but these are mapping a query, and I'm encoding the query into a vector. This vector just happens to be represented by text terms as opposed to ones. And then I can go and search for this as well. So this is a sort of another approach. It's still vector search. It's just not linear algebra vector search like you would typically think of. And so the end goal of doing all this is to parse our queries. So if you look at that top query, machine learning, research and development, Portland, Oregon, software engineer, Hadoop, Java, that first parsing is a naive text parsing. That second level is a semantic query parsing, and then that last level is a semantic query parsing where I've also expanded conceptually the meaning of each of the terms using the semantic knowledge graph to search for that term vector most closely associated with them. So we've got a lot of capabilities to do this kind of stuff in our Fusion commercial product. Not going to talk about that. I'd be happy to talk with you afterward about it. But as the last thing I want to show you real quick, and I can show you guys a live demo after the basis talks, but coming back to that query I gave you earlier, top barbecue near activate, I think I showed earlier. So just starting out with like barbecue near activate, there's capabilities in Solr to be able to actually do graph traversals. And so I've got a demo I can show you guys where I can actually type in barbecue near activate and have that parsed internally, where barbecue gets, we find out that it's in the restaurant category. We filter on the restaurant category. We understand that barbecue means barbecue or ribs or brisket, and we apply a 50-kilometer radius around the latitude and longitude that is at the venue that Activate was held at. And at a very high level, this is what my content looks like. I've crawled the web. I've got some text content. Think of it like restaurant reviews and product reviews, etc. I've got some entities that I've indexed, and I've got my some demo data with places that also includes the GeoNames database. And so when that query comes in for barbecue near activate, I can actually take near activate, understand that near is looking for some sort of a location most likely after it. Then look up activate, understand that activate is a conference. Go look up the conference entry and places and understand that it has a venue. Traverse from the venue to the actual Washington Hilton Hotel, grab the latitude and longitude of the Washington Hilton Hotel, and then run that as a search. And so I'm not going to go into the syntax here, but basically this is a graph query in Solr to be able to find the location associated with activate. So I search for the keyword activate, and I get the Washington Hilton and the latitude longitude. This is doing it as a facet with a graph traversal, same output. I'm finding the latitude longitude of the Washington Hilton when I search for activate. And then that keyword search with where I'm finding that the restaurant is the top category, and I'm finding the terms associated with restaurant where I'm filtering. This is an example of doing that as a search. And then if I put all of that together into one massive, almost incomprehensible request, I can actually do all of that in a single pass request to Solr and resolve everything that was typed into that query. And then I end up with my final result, which is top barbecue in Boston, which the vector search couldn't have handled and the keyword search couldn't have handled. But ultimately, I map it to a function query that boosts popular documents. My barbecue term vector here, filtered type of restaurant, and I've got a 50-kilometer radius around Boston. And so, there's a lot more you can do here with the knowledge graph stuff. Lots of really interesting combinations. We could go like many, many levels deep and relating these things together. But that's it for today. So, I'm at LucidWorks. We operationalize AI for the largest businesses on the planet, and I'm now going to hand it off to the basis guys. Thanks, everyone. And I'm happy to stay after them also to do questions if we have time. But you guys coming up?
So Hello, everyone. My name's Philip Blair. I'm a senior research engineer at Basis Technology. Just to make sure you're paying attention, we switched the order of the names that we're presenting in. So our talk this evening is going to be more focused on how we actually come up with these word embedding values in practice, and kind of exploring toward the Trey kind of discussed it toward the tail end of his talk, and we're going to talk specifically about some algorithms and some motivating reasons for why we would use these embeddings and so on. So first, at a high level, how do computers understand text? At the most fundamental level, text is just like any other piece of data, right? It's just a sequence of bytes. There's no inherent structure to it. So we rely on tools in order to make sense of this text in some sort of structured fashion. So for example, at Basis Technology, we have a Rosette platform where you can pass in text and get back different types of analyses ranging from tokens to sentences and so on. Then that structured data can more readily be inserted into something like a search index. Now, when you're trying to think about how this index is going to be used for queries, you're going to quickly find some problems. So suppose a user is trying to find documents about a woman who loves writing software. The naive approach to this question would be to look up documents containing all of the tokens in the query. So, i.e. you would essentially be using a term vector for this. So this works well if there's an exact match. But notice that we're more likely to return a false positive in this instance than to return this relevant document that just happens to not have any textual overlap with the query. Now, there's some ad hoc normalization tricks that you can play in order to try and mitigate this issue, such as stemming, lemmatization, and so on and so forth. But pretty much none of them, for this specific instance, are going to map this input query to the document that we're missing. So let's take a step back and think about what we wish we had instead. What if instead of looking up the tokens individually, we had some sort of semantic query of, we want to find documents semantically similar to this sentence, she loves writing software. If we had a tool to do this, then we would be able to recover the fact, oh, Sally likes to code is related to this query, and include it in our ranking and improve our search results. The good news is we can actually do this, as Trey discussed. This is where the idea of word embeddings come into play. Now, word embeddings are intuitively a way of assigning points in a vector space to words such that those points encode a semantic representation of the word. So think back to the table that Trey had in his presentation where you had different columns corresponding to, say, something was sweet or something was a drink or something was food. In the same way, the different columns of these vectors represent different semantic concepts. But the difference is that instead of being readily interpretable like that, they typically represent much more fuzzy, abstract notions of similarity that are not really simple to pin down. And so this is where, when you're comparing two word embeddings, you're typically more interested in, of course, the cosine similarity, which better reflects the semantic similarity across all of these abstract concepts. But, of course, how do you actually come up with these assignments of these vector points to words? So the methodology that arguably popularized the usage of word embeddings in natural language processing was published by Google in 2013. It's called word2vec. And so first let's briefly discuss the basic idea behind one of the algorithms in their paper. This algorithm is what's known as the continuous bag of words algorithm. And the basic idea is you're going to formulate language to fill in the blank problem. You're going to have some running window of text. Say in this case we have 3 words on either side of the word that we're currently focused on. And the fill in the blank question we ask is, given all of the words nearby, what word do we expect to be located here in the middle? The way that they do this in this specific algorithm is they take the current vectors that we have for all of these words, take their average, and then look up the most similar words to that average. Now, ideally, you would have something like this, where something like cats, dogs would have a high similarity, and cars and 7 would have low similarity, and so on. And the deep learning aspect of this is the optimization step that you're performing in which you are comparing the actual word, the current vector that you have for the actual word that you masked out, and trying to better align that average with that word embedding, if that makes any sense. The point is, given a large enough corpus, this allows a simple, unsupervised technique for coming up with representations that adequately represent the semantic space of these words. Now, a shortcoming of this approach is that you're assigning a single vector to every word, meaning that all of these vectors are forced to represent every possible sense that these words can appear in. So, for example, let's think about let's take a step back from search and think about a natural language processing task where you want to determine whether a piece of text is positive or negative, meaning like this movie's great would be positive, or this movie sucks would be negative, and so on. So if you're training a deep neural network classifier to do this task, then if you're looking at these words with a context-free representation, then the word great in this sentence is going to carry some notion of positivity, which could confuse the model and hurt your performance downstream. But instead, what we would like to do is find a way to incorporate the full sequence of text such that we come up with a representation for great which says, no, this is not positive. We're really just trying to intensify the emotion of the next word. So this sort of enrichment is where more recent advances in word embeddings come into play. So they're affectionately backronymed to be named after Sesame Street characters. And the basic idea is that you can use sophisticated neural network architectures to do a task known as language modeling. Now, this task is effectively trying to predict sequences of text in a language in an unsupervised way, which the basic intuition here is that you can take this neural network that's trained to do this and kind of stack it on top of your context-free representations in order to produce representations that better reflect the in-context versions of these words. Now, the difference between Elmo, Bert, Ernie, and so forth really boils down to differences in the shapes of these neural networks, but the high-level concept is, broadly speaking, very similar. So these context-enriched embeddings achieve state-of-the-art results in a whole variety of natural language processing tasks these days. Now, at Basis Technology, one of our specialties is in solutions for processing unstructured text in multiple languages. So as such, a particular area of interest for us is the space of multilingual word representations. So the idea here is that at a high level, you're going to have a phenomenon where when you train, the way that you train these word embeddings, if you recall, is you take a large body of English text and you get your English word embeddings, and you take a large body of Spanish text and you get your Spanish word embeddings. And the running hypothesis here is that the distribution of words in those vector spaces is actually going to have somewhat similar shapes. And so what you can do is actually leverage that fact and realign one language's word space into another's in order to actually come up with a shared multilingual vector space that allows you to do document and word similarity across multiple languages, which is very cool. So, right. So now we are going to get into our demos. But before that, I just want to, I realized I kind of breezed through some of that, but I know there was a lot of overlap with Trey's discussion, so I just want to see any questions based on anything. No? Yes. Yes.
You had a mistake. It's dog in Spanish is with double R. You have there perro, which means bear, not dog.
That's what I get for not looking it up. Okay, great. My mistake.
Oh, have a different meaning.
I apologize.
So, oftentimes when I query in a search engine, I type more than one word. And does this methodology you're outlining work for multiple word queries?
Yes, of course. That I definitely glossed over that. So all of this can be scaled up to representing documents with a variety of different approaches. I mean, you'll have some sophisticated neural networks that take in like a sequence of words and come up with a document representation. But in practice, you'll find that actually taking a weighted average of the individual word embeddings gives you a pretty good representation for the document. Of course, the former would be more suited if you're doing something like a natural language query, like, can my wife be on my insurance? But when you're just trying to do basic document retrieval, a weighted average is typically sufficient.
I have a microphone now. Are there any languages that you found are more challenging with this type of approach? Maybe if it's more tonal, or where you can get the same word but slightly different meanings using a different tone?
So are you talking about specifically the multilingual aspect, or are you talking about just word embeddings in general?
Either one, but the multilingual, yeah.
So for the multilingual approach, definitely this whole idea is contingent upon that initial hypothesis that the vector spaces are going to be similarly shaped for a very specific definition of similarly shaped. But of course, when you run into, when you're taking two languages that are very linguistically distant from one another, such as English and Chinese, then this hypothesis, it doesn't totally break down, but it definitely, it's a little rougher around the edges in practice. Things like tonality and just, word order and things like that really just compound into that issue. Okay. All right. So, in the interest of time, so why don't we move on to Gil's demos?
Thank you, Philip.
Yep.
My name is Gil Irizarry, VP of Engineering at Basis. I work with Philip. And I want to just give a little interactive demo to kind of show the concepts you've been hearing. It'll help, I think, just show what's been discussed. So I have here a very simple tool, and let me open this up a little bit. Okay, so you've heard about word vectors, and Philip before was, I can't show the vector. Okay. The word vectors are created by machine learning, right? So, obviously, as you're looking at a particular word, you've got a sliding window, and from the context, you're assigning scores. build up over time. So what that means, of course, is that similar vectors in a vector space are semantically similar words. And so we should be able to take a word and query the corpus, the library of words that we use to create the space, and find out similar words. So Trey said before, what about Advil? And sure enough, so here we've got a word-to-vec model that we've trained on just lots of news articles. And if I type Advil, I see, well, Advil's actually in the corpus. It gets a perfect score. And Tylenol, ibuprofen, Cialis, Prilosec, they're in the corpus, and the scores are going to be the cosine distance away from that canonical vector. And if I do it for other words, I type car, I get truck, vehicle, minivan. So this is a way that we can, take a word and find out, well, what are the semantically similar words? And this is not in any way that we've somehow tagged this data. This is what the machine learned just from the data we've given it. And one of the neat things that we've done at Basis, which Philip was describing, which is once I've got a vector space, and I've created it, say, for one language, and I've got another vector space in a different language, I can try to map the one vector space to the other. So here let's say I'm going to take fish. And there we go. Fish, shrimp, tuna, shellfish. Now I want to see, what is it going to tell me in Korean? And we've got a list of Korean words. And something I like to do is sort of double check it and say, well, what did it really tell me? And vegetable. Now you may say, well, a fish is not a vegetable. How did it learn that? Well, of course, how it learned any of this is through the training corpus. And I'm imagining that we gave it a lot of Korean recipes because, clams showed up, which is pretty good. And somewhere down here are herbs because I was doing this before. Yeah, there we go. So between herbs, vegetables, and clams, I think we've got a nice seafood recipe. But you can see, so the quality of this, as with everything with natural language processing, machine learning, is really the quality of the text that you input. And based on that text, we can at least see that we've made some approximation towards similar, semantically similar words. And we can do this for a variety of different languages, as we were mentioning before here. And I can, in Arabic, see what did it tell me for fish. And it actually has the Arabic for salmon. So that's pretty neat. And, if we had a library like this, and then we had a search engine, and we wanted to, at least on our own, tag documents with similar terms that people might use, we can pre-populate information around the doc and add this, or we can do it sort of on the fly. Of course, we have to worry about speed implication, but if someone's searching for fish, that person might want to see salmon, right? And if someone's searching for fish recipes, salmon market might be something that's a useful search result. So next, what I wanted to do is show another application of this. So one of the things that we do at Basis is matching names. And you might think that's an easy problem, like, are Robert and Bob the same person or not? And it turns out that names are very complicated. And one of the things that we try to do, let's say if I have a company, Eagle Pharmaceutical, which I misspelled, there we go, and Eagle Drug. So the language is the same, but if I were to do a straight string compare, which in NLP you'd call like an edit distance function, they're different words. But they kind of mean the same thing. And it could be that Eagle Pharmaceuticals is a company, and I don't remember, and I type Eagle Drug, and I want to find Eagle Pharmaceuticals. So and I just showed that we didn't do it here because I said we're searching for people. But if I say I want to search for an organization. So what we're doing here is showing that we tokenize a text and then we match the tokens, and eagle matches eagle, obviously. But drug matched pharmaceutical as an embedding match because we ran our word embedding model on it. And we found that pharmaceutical and drugs are semantically similar enough that we can raise the score. So when we were on a different entity type, we had a different algorithm that didn't include the word embedding matches at all, and the similarity score was lower. Now here the similarity score is higher, indicating that, well, maybe these are the same. Maybe this is really what the person meant. And this, the person type eagle drug, but eagle pharmaceutical might be a legitimate result. So any questions on that? It's basically, we're seeing applications of what we've been witnessing before. And so when you do this, we're taking here a vector for a word, another vector for a word, deciding if they're close enough and saying, within some threshold, they are the same or they mean the same thing. So another thing that we can do, and you've kind of heard us all allude to, is in addition to word vectors, there's sentence vectors, document vectors, paragraph vectors, as Trey mentioned. And here's an article that just showed up in the news like a day or two ago. And here's another article. So this is a bunch of MIT engineers found Da Vinci's design for a bridge, and they tested it out, and Da Vinci apparently knew a lot about bridges because the bridge works. And here's an article in MIT News that is basically the same article. But the text is different. It's not word for word the same. But semantically, they're talking about the same things. So what we can do is I'm going to take the first two paragraphs from here, and I've got this other little tool down here. And it's not very good about the spaces and the line breaks, so I'm just going to get rid of line breaks. But I'm going to take two paragraphs straight off the news, and again, I'm just going to kill the line break, and then it's going to say, well, this has similarity score of 0.8. If I were to take any other, just for, let's see, I'm taking just the top news source, don't read any political content into it, and I think I got the pop-up by mistake. Nice. All right. I'll take this. I'll put this there. Now the similarity score is near 0. So we can create an automated process that can decide if two docs are similar or not. So imagine if you wanted to do some text classification, you can have some canonical doc that is, say, science, and another doc that is, say, politics. And then you can match how many docs are closer to one or the other. Now, we have a text classification algorithm that actually works a little differently. But if you wanted to have a different way of doing both text similarity, but also text categorization, you could do it this way. And similarly, you might say, is one text a copy of another? Let's say you're trying to create a plagiarism detector. And if you're just going to go, character by character, a student could easily figure out how to thwart it. But now, because we're looking at the semantics based on the vectors, we can say, well, these two articles are pretty similar. They're mentioning all the same things. And yeah, you put them in different orders, but they've got the same entities and used in the same ways. They are basically the same document. So that was, I think we're over time. Those are just some quick demos to kind of demo the concepts and hopefully show you. None of this was about search specifically, and Trey's presentation was really awesome. But I just wanted to show, in addition to search, these are other applications that you can do. Word vectors really have taken the world by storm because they're very useful for so many things. Any questions on anything I showed? Excellent. Okay, well, thank you. I guess we still have pizza. All right, thank you.